Category O, Lecture 10, Harish-Chandra bimodules. Let's recall our setup. We work with a semi-simple finite-dimensional complexly algebra G with a fixed triangular decomposition G is equal to n minus plus h plus n plus, where h is a fixed Cartan subalgebra and n plus and n minus are nilpotent subalgebras corresponding to a fixed choice of positive and negative roots. Associated with this triangular decomposition, we have the corresponding BGG category O. In the previous lecture, we defined the bicategory of projective functors on O. Recall that objects of this bicategory are indecomposable blocks of O. One morphisms are projective functors between blocks, and two morphisms are natural transformations of functors. In the previous lecture, we also saw a theorem by Bernstein and Gelfand, which classifies all indecomposable projective functors. It turns out that such functors are in bijection with certain indecomposable projective objects in O. And the aim for today's talk is to describe the theoretical background which underlines this classification result. So to start with, we will talk about another theorem of Kostant. So let U of G be the universal enveloping algebra of G, and Z of G be the center of this universal enveloping algebra. Recall that the adjoint action of G on the universal enveloping algebra, which is defined in the following way. So for G in G, the adjoint operator of G applied to U is equal to GU minus UG. So this adjoint action of G on the universal enveloping algebra is locally finite. And we denote UG ad, the corresponding G module, obtained by considering the adjoint action of G on the universal enveloping algebra. So the following theorem is due to Kostant from 1963. The universal enveloping algebra is free as a module over its center. Furthermore, for a simple finite-dimensional G module L, the vector space hom G from L to the UG considered as the adjoint module over G. So this vector space is actually a Z module, and it is a free Z module of rank the dimension of the zero weight space in L. So this theorem is proved in the original paper by Kostant with the title Lie Group Representations on Polynomial Rings, published in the American Journal in Mathematics in 1963. So here is an SL2 example illustrating this theorem. So if you consider G to be the Lie algebra SL2, it has a standard basis F, H, and E. H is a diagonal matrix, F is a lower triangular, and E is an upper triangular matrix. And we have the Casimir element C in U of G, which is defined as H plus 1 squared plus 4FE. And we know that the center of the universal enveloping algebra of SL2 is a polynomial algebra in this element C. For k greater than or equal to 0, the element e to the power k is a highest weight element of weight 2k in the universal enveloping algebra considered as the adjoint module over the SL2. So this is simply because e to the power k commutes with e and has weight 2k. So when you commute h with e to the power k, you will get 2k e to the power k. Also recall that for a non-negative integer n, we have that the dimension of the zero weight space in the corresponding simple highest weight module Ln, which is a finite dimensional module with highest weight n. So the dimension of the zero weight space is 1 if n is even and is 0 if n is odd. If we define B to be the adjoint submodule of USL2 generated by all these elements e to the power k, so generated by the polynomial algebra in E, we will get that B is a basis of USL2 considered as a module over its center. So in connection to Kostant's theorem, it is a good time to recall the following theorem by Ovsienko, which can be seen as a generalization of Kostant's theorem. Consider the case of the Lie algebra GLN for n greater than or equal to 1. Then we have the flag of Lie algebras. G1 is a subalgebra of G2, and so on, subalgebra of Gn, where the inclusions are given by the natural inclusions of matrices with respect to the top left corner. So this flag induces the inclusions of the corresponding universal enveloping algebras. So U of G1 is a subalgebra of U of G2, and so on. And we can consider the so-called Gelfand-Zeitlin subalgebra gamma of U, which is generated by the centers of all these universal enveloping algebras. So gamma is generated by the center of GL1, the center of GL2, and so on. Please note that these centers are no longer included into each other. Moreover, they're actually algebraically independent. But directly from the definition, we get that gamma is a commutative subalgebra, and it is not very difficult to show that it is isomorphic to a polynomial algebra in n+1 divided by 2 variables. The name Gelfand-Zeitlin subalgebra for gamma comes from the following theorem by Gelfand and Zeitlin from 1949, that gamma has simple spectrum on each simple finite-dimensional G module. So this means that each simple finite-dimensional G module has a basis which consists of common eigenvectors for elements in gamma. Moreover, the corresponding common eigenvalues are different for different elements in this basis. And here's the theorem by Ovsienko from 2002. The subalgebra gamma is a maximal commutative subalgebra of UGLN. Moreover, U of GLN is free over gamma both as a left and as a right module. So note that the center of GLN is a subalgebra of gamma, so this theorem is a refinement of the theorem of Kostant. Note also that gamma is no longer central, so the left and the right actions of gamma on U do not agree. In Kostant's theorem we had a center, so U of G was free over the center, and it doesn't matter the left and right actions coincide because it's the center. But now gamma is just a commutative subalgebra, not central, and the theorem claims that U of G is free as a module over the gamma, both as a left module and as a right module. The original paper of Ovsienko is called Finiteness Statements for Gelfand-Zeitlin Modules, and it was published in the Proceedings of the Conference in 2002. Let us now talk about Harish-Chandra bimodules. A GG bimodule X is called a Harish-Chandra bimodule, provided that it is finitely generated as a bimodule. The adjoint action of G on this bimodule is locally finite, and each simple finite-dimensional module G appears in the adjoint G module X adjoint with finite multiplicity. So we denote by H the category of all Harish-Chandra bimodules. So the objects here are all Harish-Chandra bimodules, and the morphisms are all homomorphisms of bimodules. For example, if we consider an ideal M in the center of the universal enveloping algebra, such that this ideal has a finite codimension in the center, then the universal enveloping algebra itself is a GG bimodule with respect to the left and right multiplication with elements in G. So the claim is, if we take the universal enveloping algebra and factor out the two-sided ideal, which is generated by our fixed ideal M in the center of finite codimension, then the corresponding quotient is a Harish-Chandra bimodule. So that it is finitely generated is obvious because it's generated by one element. And the fact that it is a Harish-Chandra bimodule, this follows directly from Kostant's theorem. So the adjoint action of G on UG is of course locally finite. However, the multiplicities of simple modules in UG are infinite. For example, the center is infinite dimensional, and this is exactly the multiplicity of the trivial module. But if we factor out the ideal generated by a finite codimension ideal in the center, then from Kostant's theorem, it follows that each simple module will have a finite multiplicity in this quotient. So the multiplicity will be at most the dimension of the zero weight space given by Kostant's theorem times the dimension of z of G divided by m, which is finite by the assumptions. So this quotient is a typical example of a Harish-Chandra bimodule. So the universal enveloping algebra itself is not a Harish-Chandra bimodule, as already mentioned, because the multiplicity of the trivial module is infinite, since the center is infinite dimensional. For more details about Harish-Chandra bimodules, the best place to consult is Chapter 6 of Janssen's book Universal Enveloping Algebras of Semi-Simple Lie Algebras from 1983. Let us now consider some endofunctors of the category of Harish-Chandra bimodules, which are given by tensoring with finite dimensional modules. So let V be a finite dimensional G module. So we define the functor of tensoring from the left with V, and this will be a functor from the category H of Harish-Chandra bimodules to itself. And this functor sends a Harish-Chandra bimodule X to V tensor X, where the right action of G on this tensor product is given by acting only on the component X, while the left action of G on this tensor product is given by the usual coproduct formula of how G acts on tensor product of two modules. Please note that the tensor product V tensor X with the action given by these formulas is again a Harish-Chandra bimodule. Indeed, that it is finitely generated is obvious. That the adjoint action of G on this tensor product is locally finite is also obvious. Finally, if we fix a simple finite dimensional G module L, we claim that its multiplicity in this tensor product, considered as an adjoint G module, is finite. This follows from the fact that our simple finite dimensional module V is fixed, and if we consider a tensor product of V with some other simple finite dimensional module L prime, then L can appear in such tensor product with a non-zero multiplicity only for finitely many L primes. And each of such L primes has finite multiplicity in X, since X was a Harish-Chandra bimodule. It follows that the multiplicity of L in the adjoint version of V tensor X is finite. Similarly, we can define the functor of tensoring on the right with V by sending a Harish-Chandra bimodule X to X tensor V, where the right action of G is defined using the usual coproduct formula. So here this minus sign corresponds to the fact that we now consider V as a right G module. To be able to consider it as a right G module, we need to apply the canonical anti-involution, which sends G to minus G. And then the left action of G on the tensor product is given by the action on X. Directly from the definition, it follows for two finite dimensional G modules V and V prime, tensoring Harish-Chandra bimodules on the left with V and on the right with V prime commute as functors up to some natural isomorphism. Let us now talk about ad-finite homomorphisms. Given two G modules M and N, we can consider the vector space of all linear maps from M to N, and this vector space is naturally a GG bimodule. So we define LMN as a subspace of the space of all linear maps from M to N, which consists of all elements, the adjoint action of G on which is locally finite. We claim that Lmn is a sub-bimodule of the BG-bimodule of all linear maps from M to N. And this follows directly by combining the Leibniz rule with the fact that the adjoint action of G on UG is locally finite. So if we have an element of Lmn and apply to it some element from UG, we consider the adjoint action of G on this product. Using the Leibniz rule, we get the result. Next observation is that for a finite dimensional G module V, the space of all G homomorphisms from V to Lmn under the adjoint action is isomorphic to the space of all G homomorphism from V tensor M to N, and is isomorphic to the space of all G homomorphisms from M to V dual tensor N. The first homomorphism in this formula is the usual hom tensor adjunction. So if we write here instead hom CMN, this is on the node the hom tensor adjunction, and then we can notice that since V is finite dimensional, the image of any G homomorphism from V to hom CMN belongs to Lmn adjoint. And the second homomorphism in this formula follows from the fact established from the previous lecture that tensoring with V and with V dual is an adjoint pair of functors. So let us now connect category O to Harish-Chandra bimodules. We claim that for any modules M and N in O, the corresponding GG bimodule Lmn is a Harish-Chandra bimodule. By definition, the adjoint action of G on Lmn is locally finite. If we take a finite dimensional module G, we have that the space of all homomorphism from V to the adjoint version of Lmn is isomorphic, by the previous slide, to the space of all G homomorphisms from V tensor M to N. And this is finite dimensional since hom spaces in O are finite dimensional. It remains to prove that Lmn is finitely generated. We discuss it later. In fact, we will see that Lmn always has finite lengths if M and N are objects in O. So in this way, we define L as a bifunctor from O to H. So let us now discuss various categories of Harish-Chandra bimodules. Given two ideals M and N of finite codimension in the center of the universal enveloping algebra, we define H left M, right N as a full subcategory of H consisting of all bimodules which are killed by M on the left and by N on the right. For lambda in H star, we denote by M lambda the kernel of the central character chi lambda of the Verma module delta lambda, the kernel in the center. So M lambda is a maximal ideal of the center. Now, for any positive integers p and q and any weights lambda and mu, we define the following full subcategories in H. H left lower lambda upper p and right lower mu upper q as H left m lambda to the power p and right m mu to the power q. The subcategory H left lower lambda upper infinity and right lower mu upper q. So this full subcategory of H consists of all bimodules which are killed on the right by the q's power of m mu, and such that the left action of m lambda on these bimodules is locally nilpotent. So similarly, we define H left lower lambda upper p and right lower mu upper infinity as the full subcategory of H consisting of all bimodules which are killed by the p's power of m lambda on the left, and such that the right action of m mu is locally nilpotent. Finally, we define H left lower lambda upper infinity and right lower mu upper infinity as the full subcategory of H consisting of all bimodules on which the left action of m lambda is locally nilpotent and the right action of m mu is locally nilpotent. Let us now discuss exactness of the bifunctor L. The claim is that if M is a projective object in O, then the functor Lm blank from O to H is exact. What we need to show that for any finite dimensional G module V, the functor, which basically assigns the multiplicity of V in the adjoint G module Lm blank, that this functor must be exact. Note that from the previous slides, it follows that this functor is isomorphic to the functor hom G V tensor M blank. Since M is projective in O, V tensor M is also projective because tensoring with finite dimensional modules preserves projectives. So V tensor M is a projective object, so hom from a projective object is an exact functor. So therefore, this functor is exact. So the original functor of hom GV to Lm blank adjoint is exact, and this gives us our statement. Of course, for general M, from the same kind of arguments, we can only see that Lm blank is only a left exact functor. Let us now look closer at a dominant Verma module. So take a weight lambda in H, which is dominant with respect to the corresponding integral Weil group. Then delta lambda is projective in O, so this follows from the BG structure theorem for Verma modules. Recall the following theorem due to Duflo. The annihilator of a Verma module is generated by its intersection with a center. So since Verma modules have central characters, the annihilator of the Verma module in U of G is generated by the maximal ideal M lambda of the center. This theorem holds for any lambda, not necessarily dominant one. Here is the corollary. For a simple finite dimensional G module V, we have that the dimension of the space of G homomorphisms from V to the adjoint module U of G quotient with the annihilator of delta lambda, so this dimension is equal to the dimension of the zero weight space of V. So this follows directly if we combine Duflo's theorem with Kostant's theorem. Kostant's theorem says that hom V to U G is free over the center of rank dim V0. So when we kill the maximal ideal of the center, what remains is exactly the vector space V0. So this gives us this corollary. In particular, it follows that the GG-bimodule L delta lambda is isomorphic to the GG-bimodule U of G divided by U of G times M lambda. Of course, due to the action map, the right-hand side of this isomorphism is a submodule of the left-hand side of this isomorphism, simply by the action map how UG acts on delta lambda. Since V-dual tensor V lambda has a Verma flag, and the multiplicity of delta lambda in this Verma flag is the dimension of the zero space in V-dual, which coincides with the dimension of the zero space of V, the dimension of the hom from delta lambda to V dual tensor delta lambda equals the dimension of the zero weight space in V dual. So this is because now here we use that delta lambda is projective in O. And this is equal to the dimension of the zero weight space in V. So this implies that this inclusion is in fact an isomorphism, because for any simple finite dimensional module V, its multiplicity in the adjoint module on the left-hand side equals multiplicity of V in the adjoint module on the right-hand side. So let us now discuss S subcategories in O. Let V prime be a parabolic subgroup of W. Denote by X W prime the set of all weights lambda which are antidominant with respect to W prime. That is, for any reflection R in W prime, we have that R dot lambda is not less than lambda. We say that a projective object P in O is W prime admissible, provided that each indecomposable summand of P is of the form P lambda for some lambda from X W prime. The S subcategory S W prime of O is defined as a full subcategory of O consisting of all modules that have a two-step presentation by W' admissible projective modules. Using the abstract theory of recalment and centralizing subcategories, blocks of SW' are serquotients of blocks of category O. Alternatively, they can be viewed as module categories over certain centralizer subalgebras of the form EAE, where E is an idempotent, and A is the associative algebra describing the block of O. Hopefully, we will discuss as subcategories later in the course, but we will need them in this lecture to formulate the BG equivalence for categories of Harish-Chandra bimodules. So let's now discuss the main results. We start with the regular version of BG equivalence. The theorem from the original paper of Bernstein and Gelfand in Compositio in 1918, let lambda and mu be two dominant weights. Assume that mu is regular, of course with respect to its integral Weil group, and that lambda minus mu is an integral weight. Then the claim is that the category H, left lower lambda upper infinity, right lower mu upper 1, is equivalent to the category O lambda. Moreover, such an equivalence is given by the pair of adjoint functors. The first one is taking L from delta mu blank, and the second one is tensoring over U of G with the U of G module delta mu. So these are functors. The first functor, L delta mu blank, is a functor from O lambda. It starts with O lambda and it ends up in this category of Harish-Chandra bimodules. And the second functor is a functor in the opposite direction. So the singular BG equivalence then uses the notion of a subcategory in O. So let lambda and mu be two dominant weights. Assume that mu is no longer regular, but in general has dot stabilizer W prime, and we still assume that lambda minus mu is an integral weight. Then the category H, left lower lambda upper mu, right lower mu upper 1, is equivalent to the lambda block of the S subcategory SW prime via the same pair of adjoint functors. And for the proof, we refer to the original paper of Bernstein of Gelfand or to Janssen's book. So this theorem has the following consequences for classification of projective functors. So the regular classification, if lambda and mu are as above, with mu regular, then indecomposable projective functors from O mu to O lambda are in bijection with indecomposable projectives in O lambda. And the singular classification, again, if lambda and mu are as above, with mu singular with dot stabilizer W prime, then indecomposables in the category of projective functors from O mu to O lambda are in bijection with indecomposable projectives in the lambda block of the W prime as subcategory in O. And here is the idea of the proof. We should take the direct sum over all target categories lambda, so such that mu minus lambda is an integral weight, and then the outcome is stable under tensoring with finite dimensional G modules. In the case lambda is equal to mu, the identity functor corresponds naturally to UG quotient by the annihilator in UG of the dominant Verma module delta mu. So this is an identity functor with a slightly adjusted domain category. So the domain category should be adjusted not as a category O, but as a category of modules in O which have central character. And then, using this, the Bernstein-Gelfand equivalence, it matches this identity functor, or this Harish-Chandra bimodule, with the dominant Verma module, which is also dominant projective module, delta mu. And now, applying tensoring with finite dimensional modules and BG equivalence, we see that projective functors on O mu corresponds to projective objects in the corresponding category of Harish-Chandra bimodules. So here it is important that projective functors send projective objects to projective objects. In other words, we realize projective functors as projective objects in the category of functors given by tensoring with Harish-Chandra bimodules. The classification follows from the equivalence and realization of projective functors as projective objects in a certain category of functors. So here are also some other applications to the study of ideals in the universal enveloping algebra. Assumes that lambda is a dominant weight. Then the BG equivalence induces an inclusion-preserving bijection between submodules of delta lambda and two-sided ideals of U of G, which contain m lambda. Of course, the BG equivalence, it matches delta lambda with UG modulo UG times m lambda. So two-sided ideals of UG containing m lambda, they are exactly the GG sub-bimodules of the quotient of UG by the ideal generated by m lambda. And it remains to apply the BG equivalence, which map delta lambda with this quotient. Note that the ideals UG times m lambda are exactly the minimal primitive ideals of UG. So in particular, the above provides a description of the ideal structure for all primitive quotients of the universal enveloping algebra. As a corollary, if lambda is dominant and delta lambda is simple, then it follows that the corresponding quotient UG modulo UG m lambda is a simple algebra. So if delta lambda is simple, there are no proper submodules, so there are no proper ideals in this algebra. Another corollary is that if lambda is dominant, that the quotient of UG over the annihilator in UG of the simple highest weight module L lambda is a simple algebra. So this is because L lambda is a simple module. So its annihilator must correspond via this bijection to the maximal ideal in UG modulo UG times m lambda. Let us also note the following asymmetry of category O, which is revealed by the connection to Harish-Chandra bimodules. So we have the usual Chevalier anti-automorphism sigma of G. So this is an anti-automorphism which swaps G alpha and G minus alpha and induces the identity on both the Cartan subalgebra and the center of G. So using this anti-automorphism for a Harish-Chandra bimodule X, we can define X hat as the same vector space as X, but with the action of G twisted on both sides with sigma. So A dot X dot B is defined as sigma B applied to X on the left and then sigma A applied to X on the right. So we twist the sides of the action of G on X. So clearly, mapping X to X hat is an involution on H. And also clearly, for any pair of indices P and Q, which are positive integers or infinity, this involution swaps H left lower lambda upper P and right lower mu upper Q with H left lower mu upper Q, right lower lambda upper P. Observe that this involution does not leave the image H left lower lambda upper infinity, right lower mu upper 1 of O lambda in the category of Harish-Chandra bimodules invariant. So O lambda is not invariant under this involution because it will swap the indices infinity and 1. In order to have something which is invariant under the involution, we need to consider either a smaller subcategory H, left lower lambda upper 1, right lower lambda upper 1, or a bigger subcategory H, left lower lambda upper infinity, right lower lambda upper infinity. So the category O is not symmetric with respect to this involution. So for regular lambda, the smaller category with indices 1 and 1 inside the image of the category O with indices infinity and 1, it corresponds under the BG equivalence to the full subcategory of O lambda, which consists of all modules on which the action of the center is semi-simple, in other words, which have the central character. Finally, let us discuss the classical problem related to Harish-Chandra bimodules, which is called Kostant's problem. For lambda in H, we have the natural injection of the following Harish-Chandra bimodule UG quotient with an annihilator in UG of L lambda into the Harish-Chandra bimodule L lambda, L lambda. The corresponding Kostant's problem, which was popularized by Joseph in 1980, is as follows. Determine all lambda for which this natural inclusion is an isomorphism. The status of this problem is that it is unsolved in general, and that both positive and negative examples of the answer are known. So the known cases are, so if lambda is dominant, then the answer is always yes. If lambda is antidominant, the answer is always yes. If lambda is of the form the longest element in some parabolic subgroup times an antidominant weight, the answer is yes. And also, if lambda is of the form the simple reflection times the longest element in the parabolic subgroup applied to an antidominant weight, then the answer is again yes. The answer is known for rank 2 Lie algebras, and outside type A there are negative answers to this problem, and the answer is completely known for the Lie algebras SL4, 5, and 6. In general, this problem is open. So here are some questions for PhD students. Question 1. Fill in all the details in the SL2 example, that is in the proof that B is a basis of USL2 considered as a module over the center. Fill in all the details in the statement that the functor Lm blank from O to H is left exact for any object M in O. Prove that for any dominant weight lambda and any submodule n of delta lambda, the corresponding Harish-Chandra bimodule L from delta lambda quotient by n to delta lambda quotient by n is isomorphic to the bimodule U of G divided by the annihilator of delta lambda quotient by n in U of G. Question number 4. Compute the Harish-Chandra bimodule L delta lambda where lambda is antidominant. And question number 5. Use the Bernstein-Gelfand equivalence to prove that each primitive ideal in UG is the annihilator of some simple highest weight module. Thank you. See you next time.